So far in class, we've talked about how to solve simple circuits. When you get a circuit that's more complex than something that looks something more along these lines, there's two major steps to follow. First, you want to simplify the circuit as much as you can. This is what I mean by taking all the resistors and getting them all either in series or all in parallel. Right now, it'd be easy to take these two that are in parallel and these two that are in parallel, find their equivalent resistance, and those equivalent resistances will be in series. And you'll have a circuit that looks something more like this, where we have our battery here, and this would be the RT from this first side, and this would be the RT of the second part. Then we can find the total resistance of everything and solve for information that deals with the current. Once we know information about the current, we can find out more information. Eventually, we're going to use that information and make it complicated again. When we make it complicated again, we're going to expand on what we already know and turn the circuit back into its original state. We do need to get it back into the original state because we do need to solve for the current and voltage drop across each of the four resistors that we are given. Once we've turned it back into the original state, we should have pretty much all of the information that we need. As we said on the last slide, the very first step of this is to simplify it. So let's take a look at the math of this and let's start to simplify things. I know I want to draw my circuit here so that instead of having resistors 1 and 2, I end up having the two resistors as 1 marked with its equivalent. I also want to do the same thing with 3 and 4. So there's my battery. We are told originally that it's 24 volts. And here's going to be resistor 1, 2. And here's going to be resistor 3, 4. Okay, let's zoom in on resistor 1, 2 so we can get a better idea of what its total resistance is going to be. That's a little too far. There we go. Okay, we know from our discussions earlier that in order to solve for total resistance, when two resistors are in parallel, and resistor 1 and resistor 2 are in parallel, we have to use the equation 1 over RT equals 1 divided by R1 plus 1 divided by R2. So in this case, we would find that the total resistance, or at least 1 over R total, would equal 1 divided by 100 plus 1 divided by 250. When you do the math for that, you find that 1 over RT equals 0.014. But we have to remember that that's just 1 over RT. In order to solve for 1 over RT, we have to take that inverse. And we would find that resistor 1, 2 together would have a total resistance of 71.4. So I'm going to mark this as 71.4 ohms. We would have to do the same process when looking at resistor 3, 4. So we could come in here and we would put in that 1 over RT equals 1 divided by 350 plus 1 divided by 200. Again, we find that we end up with a very, very small number. It's 0.00785, but that's equal to 1 over RT. That means that RT itself is going to equal 127.2 ohms. Okay, now what we can do is think about what that means for our equivalent resistance. Our equivalent resistance here is going to be, we now have two resistors that are in series. The rule for when things are in series is to say 1 RT equals R12 plus R34. So RT, the total of the entire circuit, would equal 71.4 plus 127.2 ohms, or RT would be approximately 198.6 ohms. The next step is that we want to solve for IT, because that'll be helpful since the total current when two resistors are in series would equal the current running through resistor 1, 2, and that would equal the current running through resistor 3, 4. Now to solve for IT, we're going to use V equals IR and kind of move it around, or IT would equal V divided by R. And so we would take IT to equal 24 volts divided by 198.6 ohms, where that IT is 0.1208 amps. Like I said, that tells us that the current at R12 is going to be 0.1208 amps, and the current at resistor 3, 4 is going to be 0.1208 amps. This information is going to be very helpful, but let's zoom in on each of those resistors so we can take a better look at them. If I know what the resistance is and I know what the current is, because this is my resistance, this is my current, I could figure out the voltage drop. So I could say that from this point here until this point here, we are going to have a voltage drop. That voltage drop is going to equal the current times the total resistance. We know V equals IR. So for this location, the voltage drop would equal the 71.4 ohms times the 0.1208 amps, 0.1208 amps, and that voltage drop over resistor 1 and 2 would equal 8.625 volts. 8.625 volts. We can do the same thing for resistor number 3, 4. So we would be trying to solve for the total voltage drop from here to here. We would say V equals IR. V is going to equal 0.1208 amps times the 127.2 ohms. And my voltage drop across this portion is going to be 15.35 volts. Now a good check to make sure that everything we've got is correct right now would be to add up my two voltages. I had a voltage of 8.625 volts and a voltage drop of 15.35 volts. When I add those two together, I would end up with 23.9 volts. Now, to put that into perspective, if we refer back to the original situation here, we know that the total voltage drop should be 24. We got 23.9. Now, the reason they don't match perfectly is because we did some rounding, but that's pretty darn close. Now we can take some of this information and use it. So we want to say, you know what? I know how much voltage I dropped over resistors 1 and 2. And I'm going to take this information and I'm going to move it down. I'm going to say, you know what, that's going to be the same amount of voltage drop that happens from this spot to this spot. This has to be the 8.625 volts. Same is true here with the 15.35 volts. That over resistors numbers 3 and 4, we're going to see that same amount of voltage being dropped. From here to here, it has to be 15.35 volts. Now, since the charges themselves are either going to go through resistor number 1 or they're going to go through resistor number 2, no matter which one they choose, they're always going to have that 8.625 volts. Same thing down here. They either will go through the 350 ohm resistor or the 200 ohm resistor. And either way, they would drop the 15.35 volts. Because of this, we know the voltage for each of these spots. And when we know the voltage, it's pretty easy to solve for what that current is going to be using V equals IR. So let's zoom in on resistors 1 and 2 here. We know that the voltage is the 8.625 volts, and so we would say V equals IR. 8.625 equals current times 100 ohms, and we end up with a current equaling 0.086. Over here, we say that the voltage equals 8.625 volts. We could say that 8.625 volts is going to equal the current times 250 ohms. I would solve that in this spot. My current would equal 0.0345 amps. 0.0345 amps. Now let's follow the same process down here, solving for the currents. You would use V equals IR and the 15.35. So we would say here that 15.35 equals current times 350 ohms. Current is going to equal 0.0438 amps. 0.0438 amps. Over here, we would have 15.35 volts equaling current times 200 ohms, and my current would end up equaling 0.07675 amps. Now, I can double check my currents. The way I would double check my currents is by making sure that the two branches would add up to be what my total current through those lines could have been. If we refer back up here, we remember that our total current should have been 0.1208 amps. And we see that total current right here, the 0.1208 amps. So if I move down, if I were to take my 0.806 amps and my 0.0345 amps and added them together, we would end up with 0.120 amps. Additionally, if I were to come back down here and add the 0.04 to a 0.07, we would again be at that spot or very close to the 0.120 amps. These are just ways to double check. The basic idea, the main thing that you should pull away from these problems, and we're done with the problem now because we have the current through each resistor, the voltage through each resistor, as well as the voltage through the battery, the current through the battery and the total resistance for the battery, we're done with the problem. But what the big idea here is this idea that you simplify down the circuit. You take something that is much more complicated. Oh, I'm sorry, guys. You take something that is much more complicated. What's happening in this original situation where you have these two in parallel, these two in parallel, and this in series, you simplify it down to just having two things in series. You can solve for information and carry over some of that information to what we have when we make it complicated again. I hope this helps going through another example problem. Go through the lots of circuits and start working on those. Thank you guys. Have a good afternoon.